Hi everyone, and welcome to episode number 3 of Deep Learning Deep Dive. Joining me, of course, is my co-host Justin. Hi, Justin. How are you?
Pretty good. Excited for another episode.
Okay, great. So in last week's episode, we covered OpenAI's text-to-image generation project DALL-E, but we only had their blog post to go on, which provided only sort of like high-level information and left a lot of questions unanswered. However, last Wednesday, OpenAI followed this up with a 20-page paper filled with a lot of juicy technical detail. So we thought that it was worth revisiting this project as a part 2 and doing a deep dive specifically to this paper and to see how this project was built.
Yeah, exactly. So I'm excited to go through all the details of this. We were trying to guess a little bit at some of the technical details last week, and now we've got the paper, we've got the code, and we've got a lot more to talk about. We've also got a special guest here with us today as a third host. Aditya Ramesh is actually the first author of the DALL-E paper and project, so he'll be helping us to go through and correct any misconceptions that we have about the project.
Hi.
Yeah, welcome. Thank you for joining us. We're going to try to do our best. We've both read the paper and we're going to go through it, but we do have a lot of questions, and we definitely welcome your sort of contribution to this. As I understand it, you are basically the main author of DALL-E. Is that correct?
Yeah.
Yeah, that's awesome. So we were really excited with the paper, and we're glad you were able to join us today and help clear up anything we might be misunderstanding about the paper or anything about the project.
Thanks. Yeah, happy to help.
So then the format that we're going to follow is kind of the same as we've done the last couple of weeks, which is that we're going to go deep dive through the paper and the code, kind of section by section, and talk about any interesting stuff that popped up from there. And then we expect that will take some time. And then after that, then we'll open up the floor for audience questions.
Okay, cool. So maybe we should start with sort of like the high level, maybe a little bit of DALL-E, although we sort of covered it last time. But basically, this is a text-to-image generation project. So we are given a description in text of something we'd like to generate an image of, and then DALL-E sort of paints it.
Yeah, and in particular, like there's two interesting components here. One is a discrete variational autoencoder that is kind of compressing the image into this grid of latent codes. And then the second part is a transformer model, which is trained autoregressively to predict the latent codes from the input image.
Yeah. And so now that the paper has actually come out, kind of like the interesting part for me is this paper is, as you mentioned, it's kind of a concatenation of two papers. There's kind of like the VQVAE part of the paper, and then there's the transformer part of the paper, and they are sort of concatenated into this one system that takes the image and then decodes the image patches sort of piece by piece.
Yeah, exactly. So then the paper is kind of structured in that way, where the first part kind of gives us all the details that we want about the VQVAE portion, and then the next part gives us all the details about training this giant transformer model, and then also, of course, experiments to show how they do compared to other state-of-the-art approaches that are out there.
Yeah, and just to comment a bit on sort of we had some expectations last time when we talked, and we sort of fantasized about what the paper, when it does come out, may look like. And in terms of my expectations for the paper and like what finally came out, certainly I would say like the model is within the expectation with a few sort of exceptions that we can go over later. But what I did not expect was just how systems heavy this paper was. It gets quite intense in terms of actually getting this to work at scale, and the mixed precision details and the large-scale distributed training of the model. And so the engineering aspects of this project were very well described and quite intense, I would say.
Yeah, I had the same impression. I think that there's a lot of details that are here that are really interesting, that are almost kind of orthogonal to the goal of this text-to-image generation. A lot of the tips and tricks here around getting big, impressive models to scale on train efficiently on tons of data is sort of probably applicable to a wide class of models, not just this one.
Yeah, exactly. You can basically apply the entire transformers section to train your favorite transformer. Everything would sort of cut and paste. And the VQVA, of course, by itself also is just, it's just impressive that they were able to train it, and they describe it in detail. And just seems like that could by itself be a contribution to just image generation generally.
For sure. Also, one thing kind of looking at the text of the paper, one thing that's I'm always interested about these OpenAI projects, right? Because there's sort of two deliverables. One is the blog post and one is the paper. And it's interesting that they're written in a very complementary fashion. So the paper, like the intro of the paper, actually does not give a lot of motivation for why we would want to generate images from text. It just sort of starts off and jumps in the middle and assumes that we're all on the same page and we're ready to go and ready to solve this problem. Usually in an intro, you try to set up the problem a little bit more and motivate it. But in this case, I think actually the blog post serves that role a little bit.
Yeah. So I guess we had like a bit of an, I think that's interesting. It's kind of like written for slightly different audiences, I suppose. Like the blog post will probably be a bit more general audience, whereas the paper will be, people in the community. Okay. So we've sort of given our intros on a high level as to seeing this paper. I guess I would be curious to also hear from Aditya. Like, can you tell us a bit about sort of how this project came about internally and why you were interested in it? And I'd be curious to hear how basically this project, came to be from OpenAI.
Sure. Around the time I joined the Algos team about 2 years ago, I guess we were, GPT-2 just happened, and there was a lot of talk among like Riwan, Mark, Alec, Praful, Hibu, Christine about, how we could extend the same model class to other types of modalities. And I think DALL-E was just one of the releases that was part of that kind of discussion and thought process.
We've had this kind of hypothesis. Obviously, we're not privy to the details of OpenAI, but it kind of looks like there's this single unified code base for working with transformers and training them at scale and getting them to work on all kinds of interesting problems. And then like just applying that maybe potentially unified and powerful code base to a bunch of different things. And that was kind of one thing we were hypothesizing about this project last week.
Oh, yeah, that's not really the case. So the code base for training DALL-E, Mikhail Scott and I wrote it from scratch. And it's different from the code bases used for iGPT, and that's different from the code base used to train GPT-3. So there's a diversity of different code bases people use here. But we do try to standardize on some things too, for like data and other stuff like that.
Yeah, that's interesting. One thing that actually tipped me off slightly that this may be the case internally is that this is sort of like a 12 billion parameter model, and you go into a lot of detail as to how you actually train this effectively, in this distributed mixed precision setting. But this is actually a smaller model than GPT-3. GPT-3 is like 10 times bigger in terms of parameters, and uses this sort of model parallel training and so on. So this paper. The model in this paper is actually smaller than GPT-3, but you go into a lot of detail as to how to train it.
Yeah, there were a few reasons behind that. One, I guess, is from Mark's experience with iGPT, you only get the really sharp sample quality when you actually train the model to convergence and not to the compute optimal frontier. And so, if you do train a bigger model and you get an equivalent loss, probably, I think you would get the same sample quality as a smaller model that got the same loss as convergence, but we hadn't really de-risked that, and I didn't want to take the risk. Another reason is that, it takes a lot of GPUs to train, larger variants of this. So, that's one reason we just stuck to 12 billion parameters.
Yeah, interesting. Because you could imagine, just naively, right? Like once you translate your images into a sequence of integers, and in this case, we have the text token integers and the image integers, that's just a new kind of data set. And in principle, that should be plug and play into the GPT code base.
Well, but not necessarily, right? You're kind of mentioned down in there when you train the transformer, there's actually data augmentation going on the DVAE as well. So that means you actually have to be running the DVAE while you're training this thing, and therefore not super plug and play into like the same data setup that I imagine you have for training GPT-3.
But they're not trained jointly, is my understanding from the paper.
You mean the discrete VAE and the transformer?
Right.
No, they're not. Yeah, I spent a while doing that, but wasn't able to get any benefit in my experiments.
You do mention that in the paper. So you do just encode every image as just a sequence of integers at one point, right?
Yeah.
Yeah. So then, do you want to move on to section 2 and start getting into the sections here?
Okay. Let me see introduction. I have my iPad here. I guess one thing that jumped out. I'm just looking for the notes that I have made in the iPad. One thing that jumped out, of course, is that it's a 12 billion parameter model. The other thing in the introduction that jumped out at me is that this is a 250 million image text dataset, which is not the same as the dataset we see in CLIP. In CLIP, this was more images. So are these the same data set, related, or how are they different?
Or no comment.
There's some overlap in the composition. for example, both use a filtered subset of YFCC 100M. But overall, we built the two data sets separately with like separate goals where, CLIP was more about being able to learn from a large amount of noisy data, and I was more deliberate about the filtering process in certain ways.
Got it. Interesting.
That's very interesting. When the two blog posts came out simultaneously about CLIP and DALL-E, it definitely looked from the outside like it was sort of one unified data set that was being used for both. But the fact that you actually found it was important to collect or filter differently for those different goals, I think is really fascinating.
Okay. So after the introduction, I guess there's the method, and that's where the technical section, I guess, starts.
Actually, I guess the last point from introduction that I thought was quite interesting is this figure 1, which is showing these reconstructions from the DVAE. And last week we talked about how a lot of the outputs from DALL-E seems to have a little bit of this dreamy or over-smoothed quality. And we kind of hypothesized that this meant that we're getting much nicer images for abstract or cartoony types of outputs. And this definitely this hypothesis, and we kind of thought that was maybe due to the discrete VAE, and that seems to be somewhat confirmed by the figure 1 in the introduction as well.
Yeah, the blurriness is kind of what you'd expect from an L1 loss. Yeah, and I think a lot of the loss of quality is just because of aliasing. Like it's doing heavy downsampling by a factor of 8. So things like text and small details tend to get blurred. And if you have like, I don't know, checkerboard or crisscross patterns, it can look pretty ugly when it's reconstructed.
Right, because we are starting basically in the original image. Every 8 by 8 by 3 patch, where 3 is for RGB, will be turned into a single integer that is in the range of 1 to, 8,192. So I did the rough calculation here, and this is a roughly 118x compression. So each patch is, so there's quite a bit of compression here, and I guess we're paying for that to some extent with this blurriness because of the loss function that we are choosing in this BQVAE.
Yes.
I'm assuming actually last time when we spoke in episode 2, we briefly went into, as an example, VQGAN, which is a paper that came out recently. I'm curious if you saw that work and if you had any opinions on whether that could be used here and whether that could potentially mitigate some of these artifacts.
Yeah, that's super interesting work. I think that would be like a potentially interesting future direction to investigate. I guess the thing that hasn't been de-risked there completely is that they show that, at least with their experiments on faces, the reconstructed faces aren't exactly the same as the original ones. So I guess I'm curious that if it's scaled up on a large scale, like natural image data set, with a large enough codebook size, are you always going to get like very accurate reconstructions, or will the GAN be dropping modes or something? And I guess that's one part where I'm still not totally clear.
Got it. Interesting. Yeah, it's definitely like slightly more risky from that perspective. I guess before we go into method and the technical details, I was also still curious to hear a bit more on the high level. For you guys just looking at DALL-E, I mean, when we saw this originally, we were quite impressed because this is probably the coolest sort of text-to-image generation project I've seen so far. And it seems to work. And also I really enjoyed the image-to-image translation parts and thought it was quite magical. Like, for example, the fact that you can sort of, have a cat on the top, and then you can ask in text that there's a cat, sketched below, and the model will actually fill out, the cat's sketched or cat reflected or, in a different style. And so I find it quite fascinating and surprising. I'm wondering if, how this developed for you guys and what your overall thoughts were on the results.
Yeah, so we weren't expecting any of it. The way it worked is I just hoped that scale would be good, and I just started training the big model. Yeah, that's generally how things work. So I started training the big model, and then, time went by, and every once in a while, I'd upload the latest checkpoint to an internal Slack bot that we have, and it's usually quite busy, and everyone at work likes messing with the bot. So, so toward the end of training, people started trying crazier and crazier things, and some of those ended up as like full-blown visuals in the blog. So having that Slack channel available and a large number of people just trying stuff out to see what worked and what didn't was really helpful. I think Ilya actually found out that image-to-image translation worked. Ilya and Mikhail.
That's super cool. I think the other one that I was really impressed about were the text examples, where it's actually able to like create text, like sign with the text of OpenAI or backprop, as in the paper. I'm kind of wondering, like, how did you come up with that?
So that one I was expecting, because before the text-to-im model, before training it on a large-scale data set, we, the archive.org album cover data set that Alec trained GANs on a long time ago. I took that data set and then just tried training a text-to-image model on it to do text-to-album cover. And that worked pretty well. So I was expecting the text-to-image model to learn how to do it.
Oh, so as I recall, that data set's not huge, so maybe you actually don't need that much data for this text-to-image generation to work.
It's a lot more spotty without a lot of data, and you kind of have to do stuff to prevent overfitting, but yeah, it can still work.
Cool. Yeah, I love that you're being so unapologetic about just trying to train a bigger model. This this goes well with the bitter lesson and so on, and that we talked about briefly in the last episode as well. And also I'm reminded of the what is the meme that everyone keeps pointing to always, where it's like the neural networks person who's just like more layers, looking like a clown.
I think the graph is layers versus layers.
Yeah, I guess scaling laws are useful to the extent that you can track metrics and stuff, but the qualitative jumps in capabilities are harder to predict, and that's kind of the exciting thing about scale.
Yeah, for sure. And also, like, that image does it a disservice, because I think, like, even though from the modeling perspective, we're seeing a bit of I would say, less creativity. We found like a nice minimum with transformers, I think, in some sense, but it does a disservice in the engineering aspects. And again, like, I hope to get to that in this paper, but I would say they're quite extensive, and getting this to work at scale involved a lot of work, being creative, doing all kinds of gymnastics with different precision formats, and doing the distributed training carefully, and with compression and so on.
Yeah, I think some of the perception from the outside is sometimes like you've got this code base with your YAML config, and all you need to do is like double the number of layers and double the number of iterations, and all these magical results come out. But I think that's really not the case once you're trying to really push it, like in these projects.
Yeah, there's definitely a lot of, that's the hardest part of the project. And I think I explicitly say that, for example, like one detail about needing the per-res block gradient scaling, that blocked the project for about a month or two. Because past 1 billion parameters, the training was just getting unstable. And, with these kinds of things, there's like 100 possible causes. So then you go into a panic and you're like, oh God, why is it not working? And figuring that stuff out is not always a fun experience.
Yeah, for sure. So this is not your regular PyTorch project. There's a lot of details here, including when you guys like prefetch. You shard the model parameters across the different GPUs, and you prefetch them at just the right time and all kinds of stuff like that. But we will get to that. Okay.
All right, then should we go to section 2?
Yes.
All right, so in section 2 is about the method. Section 2 is actually the meat of the paper, where they talk about a lot of different, all the different components here. But at a high level, the section 2 intro sets up this idea that, there's two main components to the model. One is the discrete variational autoencoder that we already mentioned, that is taking these images at 256 by 256 pixels, then compressing them to this grid of 32 by 32 discrete image tokens. And then the second part is this big transformer model. And then of course the big payoff in section 2 is equation 1, which gives us this variational lower bound formula that they're claiming to jointly train these two components to try and maximize this variational lower bound on the data overall.
And I guess like on a high level in terms of the approach, for anyone in the audience who may not be as familiar, just kind of like what I find fascinating about it is the approach is that we have these transformers which are really good at modeling sequences of integers, right? And this technology works, and that's basically what GPT is, and it has a particular interpretation for what every integer is. In this case, every integer is a byte pair encoded token, which is kind of like a middle ground between characters and words. It's kind of like little word snippets. And so each word snippet gets an integer, and then we are just modeling sequences of integers. So we can basically generate, sequences of integers that have certain statistical properties. And this technology works, and we know how to train it and scale it and so on. And so any other task you may want to do, like say you want to go image to text, or you want to go text to image, or you want to go A to B or whatnot, for whatever A and B, just figure out how you can basically translate your domains into integers and then create sequences of them. And once you are in the land of just a sequence of integers, you can throw it into a transformer. So here we have two kinds of domains, text and image. So we need two approaches for how do you go from text to integers. And in this case, we just inherit byte pair encodings. So this middle ground between characters and words. The big question is, how do you turn images into just a sequence of integers? And this is where the VQ-VAE comes in, is that it is a way to turn each patch, a little 8x8 patch of an image, into an integer. And then instead of having like a large image, we just have a sequence of patches. We just stretch them out into a one-dimensional sequence. And then we concatenate those two things. So text is now just, what is the size of this? We use 256 tokens. So text tokens, 256 integers, followed by 32 times 32 times 32 integers that are all the patches. And so we just concatenate that, and now we just have a sequence of integers. And now we can throw a transformer. So I just love this idea that we just have a general technology for sequences of integers, and we can translate and encode and decode from that representation. And that's what makes this work fundamentally.
Yeah, although the extra bit here is that those sequences aren't really sequences on the image side. They're actually grids. And then when you look at the attention patterns later on in the transformer, they actually are able to make use of that. So I think it's maybe even a little bit more, this transformers are maybe a little bit more general. It's not just a linear sequence. Like there has to be some order to the tokens if you're going to model them autoregressively. But the attention mechanism in the transformer lets you put in any kind of additional information you have about potential spatial relationships among the pieces of data. And that's another reason why I think these transformers are really powerful for modeling not just sequences of text, but really any kind of set of objects in general.
Right, so in the simplest autoregressive case, when you are generating the 20th integer, it would always look at the previous 19 integers to figure out what the 20th should be. But we can actually play with the sparsity pattern in that mask. So different integers can pay more or less attention to the other integers depending on their proximity in the image or something like that. And we can encode some priors by modulating these attention masks, basically.
Yeah, exactly. And another kind of nice way that they put these two components together is through this variational autoencoder objective, right? Where you've it's kind of a standard elbow objective from a variational autoencoder, where you've got two terms. One term where you're trying to reconstruct the input data, that is the images in this case, conditioned on the text and the latent codes, and then a second term which is some kind of prior term that tries to push the prior over the latent codes that is predicted by the DVAE to be closer to some kind of closer to some other kind of prior, which in this case is the joint distribution among the tokens and the text, which is learned by the transformer. And this variational autoencoder elbow framework is a way that you can sort of mash together all kinds of different probabilistic distributions and get them to work together in a hopefully well-specified, mathematically well-grounded way.
Yep. So we have two steps. We have to train our discrete VAE, and then step 2, we have to train the transformer. So should we go into section 2.1 and talk about the VAE?
Well, actually, I had a slight question for Aditya a little bit on this elbow formulation that is being used here. So there's three neural networks in this equation. One is the encoder of the DVAE, one is the decoder of the DVAE, and the third is the transformer. But it feels to me that the discrete variational autoencoder, the encoder and the decoder there, should not deal with the text at all. But that is not what it appears to be from the equation 1. The two terms that represent the encoder and the decoder seem to involve the text. And that I found a little bit confusing when trying to really understand the elbow formulation in this context.
Yeah, that was kind of just, I guess because there's a two-stage training procedure, and just because of technical reasons when you try to formulate the elbow properly with one part using the text and one part not using the text, writing it down correctly Like, I forget exactly what the technical issue was when we were writing the paper, but there's some kind of complication with like one distribution having Y and the other distribution not having Y or something. So we just decided to write it this way and say later on that the encoder and decoder don't use the text.
Yeah, I can definitely imagine trying to write down that proper elbow could be hairy, and then you just kind of like sweep it under the rug and hope it's fine. The results are good, and the high-level approach makes sense.
Also, I think the biggest offender of Section 2, by the way, is, I have it circled in red, is the elbow, which you guys call elb. And elb does not roll off the tongue. What's up with that?
Oh, yeah, I didn't know. So I thought I saw some papers in the past using ELB, but yeah, maybe I should change that.
Okay, great. That was my only comment on Section 2.
Okay, then I guess the next section is actually learning the visual codebook.
Yes. So here we have a discrete VAE. We're going to follow the Gumbel softmax distribution. We covered quite a bit of this in episode 2. So maybe for this section, and we covered those approaches in episode 2. So maybe for this section, the only thing that was kind of interesting that I would point to is, there's a few things that kind of surprised me. Number one, the loss function, we are using this log Laplace distribution. And then we have, let's just go by them one by one. So I guess instead of just a regular MSE loss or an L2 loss in the reconstruction for the pixels, we are using the slightly fancier log Laplace. And in the appendix, there are more details given as to the motivation behind using the log Laplace distribution. In particular, that its support is only on the interval 0 to 1 where your data lies. And I think like my biggest question for this part was, is this actually something that made a difference? And if I was to only train with an L2 loss, would it be something similar?
L1 versus L2 would make a difference. The log Laplace thing was just because, I don't know, I'm kind of a fan of if the pixels lie on a bounded interval, you shouldn't use the distribution to model them whose support is the entire real line. But you could just use an L1 loss and use a slightly different weighting and it would work just as well.
Yeah, because I actually went through the math on that section, and if you look at the difference between the normal Laplace loss versus the logit Laplace here, the only difference once you get down to computing the loss is that with the logit Laplace, you end up taking the ground truth pixels that you're trying to predict, which lie on this bounded range between 0 and 1, and you invert that to make them cover the full real line using this logit function. That's like kind of the main difference once you work through the math between that and the standard Laplacian formulation.
Yeah.
But there's actually two deltas here between this logit Laplace loss versus a standard L1 loss. In addition, one is sort of you do this logit transform on the ground truth pixels that you're trying to predict. But the other detail that comes up in the appendix and not necessarily in this section is that the decoder is not just predicting the mean pixel for every output, for every pixel in the output. It's also predicting this shape parameter beta, this shape parameter b for every pixel in the output image as well. And that leads to a slightly different objective, because now once you're predicting this shape parameter, the mean is still being trained with a kind of L1 loss, but now the slope of that L1 depends on the predicted b. And on the other hand, the loss on b looks like a weird kind of, not quite quadratic, but a kind of bowl-shaped loss function as well. So I was kind of curious, even if you use the same maybe logit transform on the ground truth pixels, but omit the prediction of the b shape parameter from those distributions, then does predicting the b really matter as well?
I didn't do an ablation, so that might be interesting to try. That's a good point.
Mm-hmm. Yeah, on a high level, basically, this is like slightly an exotic formulation that I haven't seen before, and it doesn't have a lot of ablations. So yeah, I did have a lot of questions as to these details. And actually when you're doing a mean squared error loss, like a typical L2 loss, that can be seen as having a likelihood that is basically the normal distribution, where you are predicting the mean, but you are keeping the variance constant. And so here in this case, like Justin mentioned, there's this like mapping through a logit, but in addition to that, we are learning the variance basically, which is the b's. And so it's some kind of it's not clear if you want to do that. Just like when you have a normal distribution, we typically don't learn the variances. We would just learn the means when we're doing L2 loss. So that was a question for me as to whether that mattered.
Well, typically when you train a VAE, even a normal Gaussian VAE, you do make the decoder predict mu and log sigma, right? So this is kind of the analogous thing.
But I guess there, I've always kind of wondered if that's necessary, because yeah, it's the right thing. It's the probabilistically correct thing to do in that, this is a probabilistic formulation. We want the decoder to predict a distribution over values for the pixels, but it's unclear to me whether that actually matters. Whether, like, if you just do an L2 loss versus predicting the sigma as well, it's not clear how much that actually affects the results.
Yeah, and especially in this case, we ignore the variance at test time because we just take the mode, we just do the mu. And so we actually ignore the B in this case.
Yeah, I do think in the normal VAE, at some point you do need the variances to become smaller in order to maximize the elbow. So you lose out on some likelihood by not learning the variances.
That's a good point, because in a normal VAE, you actually might care about the values of the elbow and not just did I get good images at the end. So I agree. I thought the logit Laplace loss here was super interesting and non-standard, and kind of made me break out a pad of paper and a pen and work through some details, and that was fun. The other part that struck me from this section was that we finally got our answer on exactly what flavor of the Gumbel softmax was being used in this discrete variational autoencoder. Because that was a question that we had in last week's episode.
Yep, so it's Gumbel softmax. There's no reparameterization trick, as far as I can tell, although it's not explicit. The point is not explicitly made, but there's no, there's no straight-through estimator being used, is what I meant.
Yes, there's no straight-through estimator, so it is the soft version of the Gumbel softmax. But, of course, you need to anneal the temperature parameter over time. Because when the temperature is high, then this thing is very soft. And when the temperature gets low, then this approaches the hard distribution.
Right, and that is standard from the original Gumbel softmax paper, by the way. So that annealing of temperature is also found in that paper.
Yeah, but one fun detail about the annealing that is found in the appendix is the annealing schedule. So this annealing schedule is annealed only over the first 150K iterations using a cosine schedule. But that's only like that's only a very small fraction of the overall training schedule. So relative to the overall number of iterations this model trains for, this softmax temperature gets annealed pretty quickly to a value pretty close to 0, and then actually stays in this relatively almost hard, almost discrete mode for the majority of the training process.
Yep. My favorite part of this, by the way, in the appendix, where they talk about the temperature annealing, is that if you use a linear annealing schedule instead of a cosine, this typically leads to divergence. I don't know. I would just hope that would not be the case.
But cosine schedules are super trendy for everything.
Yeah, that part was kind of finicky. The reason I don't anneal over, or we didn't anneal over a longer period of time, is that if you do, the model can tend to overfit to larger temperatures. And so once you start dropping the temperature to low enough values that it generalizes from the continuous to the discrete case where the codes are no longer, softmaxes, but one-hot variables, it doesn't work that well, or it gets unstable. So that's kind of like a sweet spot there is a sweet spot for making sure the annealing stops at a given fraction of training.
That's fascinating. That's basically a tricky hyperparameter to set properly here. It seems a little finicky here.
Yeah.
I think another thing that struck out to me from this section is that, last week we complained that from the VQ-VAE paper, that in the VQ-VAE paper, it feels like it's not really a VAE, in the sense that the kind of prior term that defines, at least in my mind, that makes a VAE is sort of trivial in the formulation that they use in the VQ-VAE paper. But that's actually not the case here, because in this case, it actually the encoder for the VAE is actually predicting a true distribution over the tokens. So that means that this regularization term that pushes the predicted distribution over tokens towards a uniform prior actually matters in this case. And that's a big difference here compared to this model and the VQ-VAE model that was originally in the VQ-VAE papers.
Mm-hmm. Interesting. Yep. And let's see what else is here.
Oh yeah, that also plays into this setting of the beta parameter, right? Because the beta parameter, it gives you this trade-off between the reconstruction objective and this matching the prior objective. And actually setting the beta to be, the paper mentions that the beta needs to be set relatively high, and this to 6.6, and this beta is also annealed over the course of training. So there's another annealing schedule going on for this hyperparameter.
Yeah, that's the part that I probably didn't expect. Just reading this paper, I thought the beta would be probably fixed as a hyperparameter, but yeah, it's ramped up from 0 to 6.6 very, very early in the training, which I guess I did not expect. I haven't seen that.
Yeah, that may not be necessary. It's just a trick from Sam Bowman's old paper, learning continuous representations for sentences that I do by default in VAE code bases. So it's quite likely that if it's set to a constant, it may not matter.
That's interesting to know. Yeah, it's always hard to tell in papers like what part is like really critical and finicky and was tuned very precisely, and what part was just kind of like put there as like a standard. So it's interesting to have that color. One more thing that just a small detail, but it does matter in some cases in my experience, is this exponentially weighted iterate averaging. It is a way to squeeze out a 0.5% out of models. And so it's interesting to see that it was used here. It's basically, while we are training the model, we are checkpointing at different intervals, say every 20 to 25 updates or something like that. And then the model we will end up using at test time is a sort of weighted average of the previous iterates. And typically that's a better model through this if you sort of structure it this way.
Yeah, I've usually seen this called Polyak averaging. So I think that this term of the term they use here is a little bit non-standard for me. But I usually see that under a different term, but it seems important.
Mm-hmm. Yes.
The other thing that struck out to me in this section is that the visual codebook, the encoder-decoder, is a CNN. It's a convolutional network. And I kind of wonder, given all the kick around transformers for vision, whether they had considered or tried using some kind of vision transformer for the visual codebook as well.
I have not, but I think that would be a very interesting experiment to try.
Mm-hmm. Yeah, in this case, it's a ResNet, and I looked through the code and in the encoder-decoder. Actually, more than looking through the code, I was pretty happy with the technical detail given in the paper. I was able to re-implement, I think, good chunks of the VQVAE. I actually have it running next to me. I have a repo, deep vector quantization, where I sort of re-implemented some of the VQVAE, and I was able to train it satisfyingly. And just looking at the encoder and the decoder, yeah, I actually have it training right next to me right now. So I'm training on just 8 GPUs, but I'm training the DALL-E VQVAE. Yeah, just looking at the code, I thought it was, first of all, very clean and nice. And I love the use of adders everywhere. And yeah, it's typical ResNet and pre-activation ResNet in both the encoder and decoder. No batch norms in these smaller models, which, by the way, is kind of interesting. But is standard in these smaller models to skip that or omit that, and probably would not work with it.
Yeah, I didn't try batch norm, but maybe it would help a little bit. But typically, if I can avoid using it, I tend to not use it.
Yeah, I agree with you.
Yeah, I've definitely had trouble with batch norm in generative models in the past, where sometimes like it looks good during training, but then you switch batch norm over to eval mode and it becomes a linear operator, and the images look totally different than what you had seen during training. That the model somehow learns to overfit to the batch statistics during the training process. And that's ugly. Then like your hacks to get around that are like, one, you use batch norm in training mode during test time, which is gross. Another trick is actually to like use batch norm for the first couple epochs, and then flip the batch norm over to test mode to freeze. Yeah, exactly. And then actually train the rest of it as a linear operator. And that kind of helps you get over the optimization hump. But it's gross and it's nasty. And if you can avoid batch norm altogether, I definitely prefer that.
Yeah, it's really unfortunate that batch norm works so well in just the vanilla classification. I actually really dislike the layer, despite how well it works for classification and sort of these like more standard, deeper architectures. But yeah, anyway, that's a topic for a different day.
Actually, another interesting topic that came out from this learning of the visual codebook section, actually is in the appendix corresponding to this section, is that the atom moments, which are used for optimizing this thing, are actually stored in a custom floating point format, which I thought was pretty impressive.
Oh, is that also for the VQVAE or just the transformer?
Just the transformer.
Oh, sorry, then I missed that. I misspoke there. So the VQVAE is just trained in full FP32?
Actually, no. So most of the layers of the discrete VAE are stored in 16-bit precision, except for like the one-by-one convolutions and maybe the first and last layers of so basically the first and last layers of the encoder and decoder. But otherwise, I had enough memory on the V100s to avoid using 16-bit precision for that in moments.
Yeah, I definitely saw some mixed precision sort of keywords floating around the code base. So some parts of the model are in FP16, but yeah, definitely not all of it. Okay, cool. So I think that's section 2.1, and we have a good sense of how we trained this VQVAE. It's a Gumbel Softmax VQVAE with a slightly custom logit Laplace distribution, which may or may not matter. We're not 100% sure. There's a bunch of annealing schedules that actually make it work, and some of them are quite finicky and have to be set precisely. And otherwise, this is a nice way to train a VQVAE, and all the detail is given, including the architecture in the code release, which is much appreciated. Is there anything on the high level that we sort of have not covered in terms of getting the VQVAE to work?
Not really. I think one thing I'd add is the reason I didn't supply training code for it is because the original one was in TensorFlow. And so in the code release, we really only ported it to PyTorch because the fast code that Scott wrote to sample from the transformer was written in PyTorch already. So yeah, once I finish porting over the rest of the code, I'd very much like to release the training script for everyone to use. But I guess if you already replicated in that time, maybe it won't be necessary.
Yeah, I mean, I'm just looking at the loss function and it's not going very well, so maybe we'll still need it.
Then the next section is actually learning this transformer model that is really the meat of the model.
Yep, so now we've translated images into a sequence of patch tokens, and now we have our text tokens, and we concatenate them, and now we just have a sequence of integers. So each text image pair is just a sequence of, how many integers is it total? It's 1024 plus 256 integers. And they're just laid out in a one-dimensional sequence. Although, as you mentioned, Justin, we are going to play with the attention mask to bring in some of the priors of how these images are structured. And we're going to have like row and column and convolutional attentions. We'll get to that in a bit. But for the most part, we are basically going to put a transformer on it and model it autoregressively, very, very similar to GPT. But there's a lot of technical detail here as to how to actually get that to work.
Yeah, definitely. And one thing right, so at a high level, right, they're just training this thing autoregressively to predict the next token given all the previous tokens. But one thing that struck to me from this section is that it doesn't quite match the elbow form, the elbow again in equation 1. Sorry to keep harping you on this elbow equation. But like if you're kind of really following the elbow in a rigorous way, then you would actually want when learning the transformer, it's learning a joint distribution over the image tokens and the text tokens. And then if you're really following the elbow, then you should also be including this KL term that's trying to get it to go towards the prior. And that seems like it's not really done in any explicit way. I think it doesn't really matter. I think it makes perfect sense to just do it in the more straightforward approach here. But the formalism with matching the elbow didn't quite click for me in this section.
So you mean, I guess it's because we're maximizing it in 2 stages, right? So in the first stage, we just train the encoder and decoder. And then, yeah, I see what you mean. Because the transformer should get gradient from the KL term, even though the encoder is still supposed to.
Exactly. And that would obviously be it's not very practical to implement. But that's something you could imagine doing.
Actually, isn't the cross entropy loss for the transformer the KL term in the elbow?
Yes, but it's not quite the same, I think, because you're using argmax sampling to sample the image tokens rather than actually using the full predicted distributions.
Yes, that's true. The reason I did that, so in the underfitting regime, the discrete VAE is actually kind of nice because you get soft targets that you can use for the transformer's cross entropy loss. So it's useful for regularization. I didn't do that in this case because with the 250 million images, you're well in the underfitting regime, even with a 12 billion transformer. And it's a bit harder to fit the soft codes. So that's why I didn't do it.
I also imagine it would be a lot more practical constraints too, because that would now blow up the size of, like, if you're like dumping those things to disk and not running the model live, then it just takes a lot more space to store all of those soft codes.
Yeah. In the training code, though, we do generate them on the fly. But yeah, otherwise it would be an issue.
Okay, cool. So in section 2.2, what do we have here? So we're talking about the transformer and how we're laying out the tokens and the vocabulary size. We're going to be arranging the masks in a special way, which is covered in more detail in the appendix.
Yeah, so these masks are one way that we put in this prior back to the model that the image data are not just sequences of integers, they actually are arranged on a grid. So then in the appendix, they go in a little bit more detail on this. So that means that there's basically 3 different types of self-attention layers in the transformer model. So that one type is doing row attention. So each pixel in the 32 by 32 grid attends to the row of other tokens. There's a column attention where each token attends to the column of all the tokens above it. And then finally, there's a convolutional, sort of causal convolutional masking pattern where each token attends to a local neighborhood around it.
Mm-hmm. And of course, all of these patch tokens always pay full attention to all of the text tokens in the past.
Yes. One thing I found interesting from the appendix is the arrangement of the different sorts of attention layers within the model. So this model is a 64-layer transformer model. But in that, the causal masking attention only is the very last layer of the model. And then the row and column attention is the entire, all but the last layer. And there's row attention for most of them and column attention only every 4th layer.
Right.
And I thought that was a little bit of a funny pattern here.
Yeah, it's row, row, column, row.
Yeah, that's copied directly from sparse transformer. So it's not my idea to do row, column, row, row. I think V1 figured that one out. My one change was adding the convolutional attention at the end of the model, which I think was Scott's suggestion. And it makes the loss like a small amount lower compared to using the normal pattern for the last layer.
I was also wondering in the non-equal treatment of the row and column attention, my guess is that the column attention actually should be more computationally expensive because, as is mentioned in the appendix, you actually need to transpose, a transpose on the data in order to efficiently implement that column attention on a GPU. So even though these are logically kind of equivalent, I would expect that the column attention is a little bit slower to run in practice. And maybe that might be why you use more row attention than column attention.
I think it's actually because it works better in practice.
That's disappointing.
That is kind of surprising. You'd expect images to be sort of like symmetric in X and Y directions, basically, so...
But it's not fully symmetric because the row and the column are a little bit of a misnomer. The row is actually attending to the previous n tokens in raster scan order, so it actually wraps over to the previous row, whereas the column is like only attending to the column directly above it. So the row attention is actually looking at more stuff than the column attention in most cases.
I guess we have just some sparse attention patterns here, and I think, there's a lot of ways to play with this, with the setup here. But there's no like detailed ablations or anything like that. But you do want sparse attention because, of course, it's much more efficient because we don't have full all-to-all communication. We sort of sparsify it so that it's more efficient.
The other thing I'd mention is you actually get a lower loss with sparse attention than you do with dense attention.
Oh, that is interesting. Okay.
Yeah, it's noted in sparse transformer. So there's optimization problems typically, which are kind of weird.
So I guess that's like, if we put this prior into the model, it's actually useful for making it learn better. It's not just constraining it for engineering or implementation reasons.
Yeah, exactly.
Okay, interesting. Not obvious. And then, okay, so we're manipulating the masks. We're coming up with a way to represent sort of these padding tokens. Like, what do we do when we do not actually reach the upper bound of 256 tokens? So that all makes sense, I think. One thing that I definitely found kind of surprising is that when you are talking about the loss function, you actually have a loss on the text weighted by 1/8, and not just a loss on the image itself. So we actually are training on the text as well, even though we're doing text to image.
Yes. The reasoning for it is, I think in small scale experiments, I did notice it was just helpful in terms of sample quality for some out of distribution examples. And I figured it was like a useful regularizer to use since it's a lot easier to, I don't have a great explanation for it, but typically, I guess in the text to im literature, you see I don't know, previous work with GANs having some kind of loss to help encourage them to learn a good text representation.
So it's like an auxiliary loss.
Yeah, exactly.
But that also means that because of this structure, you could ask the model to generate unconditional samples where you don't give it any text. It both invents its own caption and then invents an image that matches that caption. And I think it'd be kind of interesting to see fully unconditional samples from this thing.
Yeah, that is a possibility.
Yeah, so that's one thing I found surprising, because I would expect, just naively, if I was re-implementing this model, I would not apply loss on the text because we're doing text to image. So my first loss would be on the first patch of the image. So that was kind of surprising to me, and I guess kind of interesting. And the claim here is that it's acting as a auxiliary loss and improves the overall objective. Even though there's no there is no overfitting, we're underfitting in this model. So maybe it's not clear to me that I would expect that, basically.
Yeah, we don't have an ablation for that, unfortunately, just because I kind of just had it as a implementation detail pretty early on. And but it would be interesting to repeat that for a larger model and see if it makes a difference at scale.
Another thing that came out in this section is the precise architecture of the transformer that's being used. So I noticed that it's a 64-layer model, and in each transformer, the dimension of the heads are 64 dimensions per head, but there are 62 heads per layer. And I wonder, it would have been so nice if this was a 64-layer model with 64 heads and 64 dimensions per head, and it would have made everything match. So I wonder, did you just barely run out of memory and couldn't fit those extra 2 heads into the memory of the GPU?
Yeah, so we squeezed so much memory out of the TensorFlow code base that we were down to, I think, 20 megabytes. That's
Nice.
Another reason why we stuck to 12B. Because on the old Google clusters, it was much less efficient to do parameter sharding over machines. And I didn't want to add support for that at the time. So instead, we hyper-optimized the code base to fit the largest model possible on just an HGPU machine.
Mm-hmm. That's really funny. Whenever I see numbers like 62, I typically get a little bit nervous because it's not a multiple of 8. So I'm just not always, but yeah, I guess this is the upper bound of what we could fit in the GPU. That's really funny. So we can continue to section 2.3 maybe. Before we do that, actually, I wanted to scroll back up in the paper. We actually skipped figure 3. Can we briefly go to figure 3 before we talk about data collection? So in figure 3, we have a few examples, and we are showing the actual ground truth image that goes with every caption. And then we are showing the generation from the DALL-E paper and some baselines. And DALL-E, of course, looks significantly better here. One thing that I found kind of interesting was I wasn't sure how much to dig into this, but on the 4th caption, it's a living room with a TV on top of a stand with guitars sitting next to, and then it's empty. And so I wasn't sure why this is cropped in the text. Did we run out of byte pair encoding tokens, or is this some kind of artifact of the data set?
We created these, so I wasn't the one who made this particular figure, but I'm assuming it's probably because that's just what the ground truth caption from Coco was.
It's just cropped like that.
Yeah.
Oh, okay, interesting.
Really high quality data there in Coco.
Yeah, I wasn't sure how much to read into that detail. I just sort of circled it and I thought about it for 10 minutes. Okay, cool. Okay, let's go to section 2.3 then. This is where we are talking about data collection. And then in the appendix, there's another section that talks about the details of the data collection. But I think it's a little bit of a misnomer because not a lot of detail is given, of course. Yeah, I guess we don't know, in the clip paper and also in this paper, we do not know a lot about the data, how it was collected, and of course, the data here is incredibly important to making the system work. And without it, if you only had MS Coco or something like that, you would not be able to train the system. So it's kind of interesting that these sections are unfortunately slightly too short, maybe. And of course, the data sets are not available.
Yeah, I think one thing I will say, though, is you could reproduce the results to a pretty satisfying level of quality on conceptual captions. I mean, you won't get all of the capabilities that DALL-E has, but it's enough images to get the system to work and see some examples of out-of-distribution compositionality. So the initial results I had and the data set I was using for the first few months was actually just conceptual captions.
That's really good to know, because conceptual captions is a pretty standard data set in the vision language community these days.
Yeah.
Okay, cool. So maybe let's go into section 2.4 and 2.5, which for me are kind of like the meaty components of the gymnastics we go through to scale this model and actually train it. So maybe starting with the mixed precision.
Yeah, so in mixed precision, right, like there's this, so something like a V100 can operate in this mixed precision mode, right, where it has tensor cores. The tensor cores can compute the multiplications in 16-bit, but then accumulate into 32-bit. So a lot of people, when training on V100s these days, are making use of these either fully 16-bit low precision modes or these mixed precision modes that are enabled through the tensor cores. And it seems that this was done pretty thoroughly throughout the entire model, that like almost anything that could be put into 16-bit, that's pretty much anything compute intensive or memory intensive, is being put into 16-bit low precision. And that's going to both save compute. That's going to make things faster because it lets you hit the tensor cores on the V100s and make everything faster. And seemingly very important for this model, it's also going to save a lot of memory, right? Because as you just said, you were really like pushing the boundaries of the memory limits of these GPUs, and storing those activations in lower precision obviously uses half the memory.
Yep, an additional benefit of this, of course, is that we are reducing the memory bandwidth required to work with the model. So we're up to halving it because we have only FP16 sort of quantities to work with. And of course, a lot of these applications can be memory bound. And so we don't want to fetch and store a lot of things to the DRAM when working with these models.
And then, of course, some other standard tricks here, like activation checkpointing, where you actually, instead of storing the outputs of every layer during the forward pass to reuse them during the backward pass, instead you are going to recompute some of the layers during backpropagation, which is another way to save memory but spend extra compute. Although one little nice detail here is that this is often called gradient checkpointing, this idea, but they call it activation checkpointing in this paper, which actually is a better term because the activations are indeed the things being saved, not the gradients. Yeah,
for sure. I think this always confuses people because, checkpointing, the checkpointing itself also is kind of a confusing term. People almost always think about the actual checkpoints of the model. But here, so we're checkpointing intermediate activations and then recomputing things so that we don't have to cache them for the backward pass. But I think on a high level, kind of as you said, these are NVIDIA V100 GPUs that only have 16 gigabyte. So maybe a more standard V100 would have, say, a 32 gigabyte, or indeed now we have 80 gigabyte GPUs. But here, 16 gigabyte is actually quite low, and we have to fit this model into this budget. And this is kind of like a primary, just a driving force of really squeezing out the juice here and using half precision for as many parameters throughout the model as we can afford. And we are quite surgically precise in what parameters we actually allow to be used in half precision and what parameters we are constrained to use in full precision. And so I thought the paper goes into a lot of detail of what exactly is and is not in FP16, and there's a lot of detail here basically to save all the memory that we can.
Yeah, the primary reason for it, some of it was just to save memory. But as I mentioned earlier, I think the hardest part of the project was just getting the model to scale reliably past 1 billion parameters. And we found after a lot of pain and suffering that the root cause was actually underflow, which normally when you use float 16 on a GPU, floating point format is kind of like you have a real number line and then you have tick marks with the tick marks being closer together near zero, and then the spacing between consecutive tick marks increasing as you get away from zero. So what underflow is when you're doing backprop or some kind of computation in the model, if a result is too close to zero, meaning that its value in arbitrary precision would be in between the tick mark for zero and the closest tick mark next to that, it gets rounded to zero. And the problem is with the 16-bit format that's supported on V100 GPUs, you don't have that many bits of exponent, which means the tick marks are spaced relatively far apart compared to what you would have for just normal 32-bit precision. And so these guidelines and all of this care about where float 16 is used and these specialized formats and the per-res block scaling was to try to avoid underflow wherever it could be happening in the model.
Yeah, and one thing I thought was really interesting here is like I almost felt like I felt so sorry for you that you had to work with this 16-bit format that is used on V100s, right? Because the V100s use this FP16 format that only has 5 bits of exponent and 10 bits of fraction. And it seems that we've been moving away from this particular 16-bit floating point format for mixed precision, probably due to all these exact underflow reasons that you're talking about. So the TPUs and also the newer A100 Ampere GPUs from NVIDIA actually support an alternate 16-bit floating point format that allocates 8 bits to exponent and only 7 bits to the fraction. And I just wonder, like, you know, for people that are trying to duplicate this work a year from now, and they do it on something that supports this BF16 alternate format, I wonder if that would just make a lot of these problems magically go away.
Possibly, yeah. I will say that I guess one potential disadvantage with bfloat16 is that you have fewer precision bits available. So if you're doing, let's say, an all reduce over a very large number of machines, the error in that all reduce is going to be the log base 2 of the ring size. And so it's easier to get garbage results if you add up a lot of numbers. Or let's say you're storing your activations in bfloat16, but your model has, 256 layers or something. Then as you add the contributions from the res block to the identity path, after enough additions, you might not have any good bits of precision left. But generally, I think it's a much better default format.
And then if I'm putting on my Jensen Huang leather jacket, I'm glad you brought that up because, the new Ampere GPUs actually have another floating point format that kind of gives you the best of both worlds, which is this TF32 format that both has the 8 bits of exponent from BrainFloat16, but also the 10 bits of fraction from FP16. And that's a kind of weird 19-bit floating point format, but that's one of the main selling points of the new Ampere GPUs. So that feels like a pretty appealing thing to play with in the next couple of years.
Mm-hmm. Yeah, so I definitely found it interesting. Like typically when you want to train in half precision, you would just hope that this would be automatic. And, PyTorch has support for using standard loss scaling, where we just scale the loss on the top and we sort of hope for the best. But as is mentioned in this paper, once you actually reach larger model sizes, this may not suffice to do just the scaling basically at the loss layer because your model shows a lot of dynamic range between the different layers of this ResNet for these gradients. And so you guys actually end up using this per res block gradient scaling trick, which in this case ends up being very important to basically normalize these gradients more carefully and shift them to the FP16 range per residual block. So I haven't seen too much of this. And so it's kind of interesting to see that here as like a necessary component.
Yeah, and the odd thing is it shows up at different scales for different model types. So even CLIP, when it's scaled up past the size that's reported in the paper, also needs per res block gradient scaling, along with other kinds of models that we've tried to train.
Interesting.
This section also reminded me a little bit of the normalizer-free networks paper that came out fairly recently. That was quite different in what they were doing. They were trying to get these really deep models to train without any batch normalization. But one of the findings there was that as you go deeper and deeper in these ResNet blocks, then the variance is going to grow monotonically over the course of many residual blocks. And to kind of counteract that growth in the variance over many residual blocks, in that paper, they also resorted to inserting a little multiplicative scalar at the end of the residual blocks. But the other thing that happens in the NFNets paper is that because it's a convolutional network, there are downsampling blocks. And in the downsampling blocks, it's not fully residual anymore. Instead, you've got a one-by-one convolution to connect between those different scales. So then in this NFNets paper, these downsampling plots are really important because they let you reset the variance of the activations back to a desired range. But for a transformer model, you're not getting that property. Instead, it's just a giant stack of transformer blocks all the way, and there's no opportunity in between them to ever reset the variance.
Yeah, that's true. I think it would be interesting to see if a better init or some kind of alternate transformer module design could avoid the monotonic growth in variance.
Mm-hmm. Yeah, and you guys mentioned that very briefly in a sentence in the paper.
I mean, and just thinking at a more high level, all this section around about floating point formats, I think just shows us how leaky some of our fundamental abstractions are, right? That we often want to think that we're doing math and we can just think about real numbers as they are with all their nice properties. But once you really want to train these big models and squeeze everything out of the hardware, this leaky abstraction of how do we even represent numbers on a computer is something that you actually have to pay close attention to. And that's always pretty interesting to me.
Yeah, I mean, you could always just train with FP32, but then you're leaving performance on the table. And FP32 would, of course, maybe not run into these issues as much. You have many more bits for exponent mantissa.
Then the other part that came in here is actually they're also storing the atom moments in 16-bit precision in a 16-bit format as well. But what I found really interesting about the atom moments is they're actually stored in yet another 16-bit floating point format. So we talked that like the normal FP16 floating point that the V100 supports has 5 bits of exponent and 10 bits of fraction. But Atom actually uses 6 bits of exponent and 9 bits of fraction, plus 1 sign bit. And then the variances, variances are always positive, so we can throw away the sign bit and give that extra sign bit back to the fraction. So clearly this is some really intense low-level GPU hacking to implement your own custom floating point formats.
Yeah, I was thinking of Scott Gray when I was reading this. Yeah, so Scott Gray magic here to squeeze out extra performance. But yeah, I think, Justin, that's a really good and interesting point on a high level, that if we really want to squeeze out the juice out of these models, it's we have to really think about not just real numbers, but how these numbers are represented on the computer in a lot of detail. And it's kind of interesting that you can get away with lower precision in these like arbitrary parts of the network, but you really have to use higher precision in other parts of the network. And you have to be very careful with tracking the gradient and activation and weight magnitudes all over the place in the network. And it kind of just gets a little bit complex from that perspective.
All right, I think that was all the main stuff with mixed precision training, which is super cool and super interesting. And like we mentioned at the top, a lot of these ideas are applicable well beyond this project. All of these things are kind of just like best practices for working with mixed precision in big models that could be applied anywhere.
Mm-hmm. And in this case, transformers specifically as well, because of the residual sort of structure and so on.
All right, so should we go on to the next section on distributed optimization?
Yes. So of course we have a cluster. We have relatively fast intra-node communication between GPUs, but a relatively slow inter-node sort of communication between different nodes, and we have to deal with that. And this becomes one of the major training bottlenecks, allegedly, according to the paper here, to training the model. So we're spending a lot of time communicating gradients between the different machines and synchronizing them to basically do the all-reduce operation.
Well, there's that. There's also the problem that the model is just too big, right? So if you've got a 12 billion parameter model and you store the whole thing in 16-bit, that means that each parameter takes 2 bytes. So then you need 24 gigabytes of memory just to store the parameters of the model. And that's trouble because we're working with 16 gigabyte NVIDIA V100 GPUs. So that's no good, right? Because the normal way that we distribute work across GPUs is using data parallelism, where we run the exact same model on all the GPUs and across all your machines, but each GPU operates on a different batch of data, and then you do each GPU does an independent forward pass and backward pass on its own batch. Then they all communicate gradients, do an all reduce on the gradients, and then make a gradient step. And then at that point, they all have their own local copy of the parameters, but they're all kept in sync due to this all reduce operation. But this doesn't work in this case because here we want to train a model whose parameters are larger than the size of the memory of any individual GPU. So we're in big trouble. And keep in mind that we need to use the GPU memory not only to store the parameters, but also to store the gradients of the parameters. And we also need to store the activations of the model, at least some of them, for doing this forward and backward pass. So we are in big trouble now if we want to try and train a 24 gigabyte model with only 16 gigabytes of memory on our GPUs.
Yeah, so 2 primary tricks used here are, number 1, as we mentioned, this is the activation checkpointing. So as we are doing the forward pass, typically you would cache every single intermediate activation in memory in preparation for the backward pass later, because you will need those activations. So here we are going to be throwing out a lot of them, but we're going to be keeping some of them. And then during the backward pass, we are going to be recomputing the forward pass, or small chunks of the forward pass. So that's one way to save, pretty standard when you are training these very massive models. The one that I've seen less frequently is this figure 5, where they talk about the parameter sharding across the GPUs. So as you mentioned, this model does not fit on any individual GPU, so we are going to spread it out across the GPUs of a single node. In this case, we have 8 GPUs per node as a standard. And then we are going to intelligently pre-cache prefetch the activations as we're doing the forward pass, and we're going to be overlapping the communication with the computation of the individual residual blocks. And this prefetching is done both during the forward pass and during the backward pass. So again, this is like a major deviation from just a typical PyTorch module, NN module that you would like train in a standard setting. And this is again where the HPC components of what we're doing here are really, on display again.
Yeah, for sure. I thought this parameter sharding is super cool. I was actually not super familiar with this setup before reading this paper. And to me, it feels almost like a smarter version of model parallelism. Because we normally do data parallelism and run one copy of the model on each GPU. But then if you want to train a really big model, another appealing idea is to split the layers of the model up across different GPUs. So you have like GPU 1 compute the first 8 layers and then pass the results to GPU 2 to compute the next 8 layers, and so on and so forth. And that also allows you to split up the parameters across all of your GPUs, and none of them need to store all of the model parameters. But this naive model parallelism is terrible for performance because most of your GPUs are sitting around doing nothing but waiting for their turn to compute. So this model parallelism is a kind of dumb way to split up your model across many GPUs, but it's extremely inefficient in terms of wall clock time.
You could try to, and I think some papers do, pipeline on the next sort of examples to keep most of the GPUs busy. But I do think that the complexity of the code grows quite a bit. But I sort of agree with you that this is kind of like a hybrid approach between data parallel and model parallel that I haven't seen before, and it's quite interesting.
Yeah, so then the idea here is you're going to divide the parameters up of your model up into 8 subchunks, and each parameter will be owned by one of the 8 GPUs in the model. So now, like, that GPU is going to be responsible for dealing with those subset of the parameters. But now in each forward pass, we're going to operate in a data parallel mode. So each GPU will get its own local batch of data. But now we have trouble because each GPU wants to work independently, but each GPU doesn't have the full model. So then right before each layer is executed, the GPUs need to all talk to each other. And the one GPU that owns the parameters for the layer about to be executed needs to send those parameters to all the other GPUs on the machine. And then now once that is done, then the GPU can compute that layer. And then once it's got the activations, then the GPUs that don't own the parameters for that layer are going to throw them away and free that memory. And then this whole operation needs to happen again in reverse during the backwards pass. And this is all interleaving with the computation. So this is just like crazy to implement, that you've imagined that like all of the GPUs are talking to each other before every layer in both the forward pass and the backward pass. And this is all happening in parallel with the computation. This seems extremely challenging to implement efficiently.
Right. So one note here is this is one thing that's actually easier to implement in TensorFlow than in PyTorch, because TensorFlow does the asynchronous kind of execution for you.
Interesting.
That seems like something that we should get fixed.
I know PyTorch had some, basically was incorporating model parallel training and primitives for communication into the framework. I just don't know how far along they got in terms of support for something like this.
Yeah, and I think their all-gather and reduce-gather until perhaps recently had some, were using too much memory and had certain performance issues. But yeah, I think they're getting fixed up.
Mm-hmm. And I also, the other thing here that I would like to note is that we talked about mixed precision training and how that was important, and now we're talking about the distributed optimization. There's also a paragraph here on how the joint of the two have to interact. So you have to actually co-design the optimization with the mixed precision training, and you have to be careful because some of these are in reduced precision, and when you're doing the all reduce, you don't want things to underflow or overflow depending on how you do them. So there's a lot of like co-design, I would say across the distributed optimization components and the low precision components of getting this model to train. So it's just kind of heavy. It's like, wow.
Yeah, you have to figure out all the details.
So then the next big interesting chunk in this section is this idea of gradient compression. Right? Because we know that, as we said, when we're doing this model parallel training, or this data parallel training, then each GPU is sort of computing a local gradient for its own batch of data. And then in order to make your SGD step, you need to do an all reduce to communicate those gradients between all the GPUs, not just in a single machine, but really across all the GPUs in the entire, all the 64 GPUs that are being used to train the model. And this step is pretty expensive because now you need to communicate all the parameters, because now the gradients are going to be the same size as the parameters. And that's like 24 gigabytes of data that needs to be sent out from each GPU and all reduced onto all the other ones. And that is a huge overhead because now you've not got to send all this tons of gradient over the network on every training iteration. And now they have a very clever trick to overcome this, which is this idea of gradient compression. So that each GPU, before we do the all reduce, each GPU is going to do a compression operation on its own local gradients. So that instead of sending the full gradient around to all the other GPUs, instead we're going to compute some low-rank approximation to the full gradients that we want to compute. And the particular formulation of gradient compression is this Power SGD paper from NeurIPS 2019 that actually I had not seen before, and I read that paper as well. I thought it was a very, very nice idea.
Mm-hmm. Yeah, I skimmed the paper and looked at figure 1, but I mean, that contains the main idea. I didn't dive into all the detail because there is quite a bit of detail, but on a high level, we are computing this low rank approximation, and we are doing it keeping in mind that this has to be very, very fast. So this compression has to be quite fast because we are sort of, again, this is the sort of bottleneck of the model training at this point.
Yeah, so normally the way you would compute a low rank approximation to a matrix, like you'd learn in a linear algebra course, would be to do a singular value decomposition. But that's going to be way too slow to do on every iteration of the model. So instead, they have this kind of nifty iterative algorithm called Subspace Iteration, which is an iterative algorithm for computing approximate low rank approximations to matrices. And the clever part here is now each iteration of a stochastic gradient descent, you only do one iteration of this iterative subspace iteration method. But now you warm start, so you actually interleave the computation of the low rank approximation with the stochastic gradient descent updates. And that's quite a nice idea that seems to work quite well in practice in this setting.
Right. And actually the appendix, by the way, has a huge amount of detail on Power SGD and all the details here. This is pages 17 and 18, implementation details of Power SGD. And I definitely admit to at most skimming this section because this looks quite intense in terms of the implementation here.
Yeah, and this Power SGD seems not to be a standard thing that people are doing. Like this paper, I think at the moment only has like 44 citations. So it seems like kind of a gem out there that you somehow found and picked up, and it seems to give you a lot of juice in this setting.
I think we were discussing the topic of whether, how gradients could be compressed, and had the idea of maybe using subspace iteration. And we looked online, and Mikhail, I think, remembered that he came across a NIPS paper that was proposing to do the same thing.
Interesting, because then it definitely seems in your setting you had to scale this Power SGD method up way more and deal with a lot more implementation details than were present in that original paper.
Getting it to work at scale required a lot of care to fix a bunch of performance regressions.
Yep. And like you mentioned, Justin, a lot of these techniques are quite general and can apply to a lot of other models. So again, this is, an example of something that can be probably used more widely. And we do get, it seems to be about an 86% compression rate out of it. And so that I imagine is quite helpful because I imagine it's actually a quite standard setting in some cloud GPU provider that your node-to-node communication is not going to be super fast. This probably is a bottleneck, I think. Okay, I'm not as familiar with the cloud providers, but I imagine this could be a pretty common bottleneck.
Yeah.
Yeah, so I think those are the two major points for me in this section. One was the parameter sharding, and the other was the Power SGD gradient compression.
Mm-hmm. Yeah, that's right. And so now we go to 2.6, sample generation. This is where we start to get some of the experimental. Actually, in the sample generation, we just talk about the fact that so we actually, when we do text to image, we don't just do a single shot of sampling autoregressively to get the image. We actually generate 512 different images for any one text caption. And then we use a third model, in this case, CLIP. And CLIP is a contrastive model, so it takes a pair of image and text, and it gives you a single score that tells you how well they match together. And so we first generate 512 candidates, and then we re-rank them using CLIP and take the one that looks best. And so this is quite, I imagine, important to get some good results. And they have a few examples here comparing it and looking at the FID scores and the inception scores and how they vary as a function of how many images we actually are generating independently.
In particular, figure 6 here is pretty cool. So in figure 6, it shows us the effect of, how many samples do we take for this re-ranking. And then let's just look at the best sample among a different number of samples. And when we just look at the absolute best of one, that's like the first thing generated by the model, then they actually don't really match the caption that well in many cases. But once you go to 512 samples, it seems that it's able to explore the space much, much better and actually give you pretty good captions, pretty good results at 512 samples. So then, I mean, I always wonder with things like that is like, how much diminishing returns is there? Like if you go to 1024 or 2048 or 4096, do the sample quality continue to improve?
For some things like with the text, it does help to use more samples for re-ranking. So when doing things like writing text, if you use a very long word, generally the longer the word, the lower the success rate. But if you re-rank using a larger sample size, you can still get it to work reliably. For other things, there tends to be a diminishing returns for sample quality past 256 or 512.
Mm-hmm. We actually do have plots in figure 9C that show, as a function of the sample size for re-ranking, what happens to the FID scores, for example, and the inception scores, which are the two metrics for probing the visual quality or fidelity of these images. And these are basically like perceptual losses, FIDs at least. And so we see that we get better performance in terms of the FID metric for until what looks like n equals 128 or 256. And then we actually slightly go up.
Yeah, but these metrics are super coarse and they don't really correlate. No, I don't really trust these metrics. They're the best we have, but they're pretty far from perfect. So I'm more interested in like the perceptual of people who's, Aditya's spent probably many hours looking at samples from these things, and what's his impression of the diminishing returns is much more solid evidence to me than FID or IS numbers.
I accept that.
One thing I would add is now that Clip is open source, it might be interesting to try a variant of FID based on using the Clip embedding space instead.
Oh, that's a good idea. Yeah, because both of these metrics are kind of agnostic to the model that you're using. I guess Inception Score wants a distribution over categories, but FID just needs features, so you could do that on any CNN.
Yeah.
Mm-hmm. That's an interesting idea. Okay, cool. And then we have data overlap analysis, just making sure that we cross the T's and dot the I's, important. And then qualitative findings. Of course, qualitatively, the results are really good.
Then the quantitative performance is, of course, DALL-E is an amazing project, but they're certainly far from the first to try to tackle text-to-image generation. This has been a pretty popular topic in, CVPR the last couple of years, and they do a pretty good job of trying to compare with what is basically the state of the art on this problem on Coco and this CUB birds dataset, which are the two datasets that people usually work on for this problem.
Mm-hmm. And they specifically focus on, I would say, zero-shot performance, right? Which is a good thing and is quite typical in OpenAI papers recently.
Yeah, exactly. And that's a pretty critical distinction, right? Because these existing models, they're trained on the Coco training set and then they're tested on the Coco test set. And the Coco training set and Coco test set are pretty particular, right? They're not general language. They're a specific type of language that was constructed by workers on AMT with particular incentives and particular instructions. And it's pretty nice to see that this DALL-E model can generalize to the type of language being used on Coco test set, even in this zero-shot setting of not seeing any particular form of that language during training.
Mm-hmm. Yeah, and that basically kind of concludes the paper. Is there anything else here?
Because I've worked a little bit on these, text to image or image generation problems before, and they actually don't beat the state of the art. So when they do, especially zero-shot performance on Coco, some of the existing models actually do a little bit better than DALL-E in terms of inception scores and FIDs. But there's an interesting argument here in the paper is that, these FID and inception score metrics are super sensitive to high frequency detail in the images that are being generated. And we know from our earlier discussions that the VAE formulation and the L1 loss used to train the VAE lead to a little bit of over smoothing in these image results. And most of the other competing approaches here usually use GANs, which generally make don't suffer from this over smoothing problem as much. So a kind of nice trick to have in your tool belt as a researcher is that when you don't win on the metric, then you change the metric. So they changed the metric a little bit. And in addition to comparing the raw images coming out of the model, they also try blurring the images, both from the DALL-E model and from the other prior approaches, blurring them with various increasing amounts of Gaussian blur. And then we get some kind of interesting results, is that when you look at the raw images coming out of DALL-E and these other approaches, then some of the prior work actually beats DALL-E on these automated metrics. But once you kind of try to correct for this over-smoothing effect by blurring all of them, then actually the trend flips, and DALL-E images then start to outperform the prior work on these automated metrics. And I thought that was a pretty interesting analysis that I don't usually see in these image generation papers.
I see, got it. Justin, you're probably more familiar with the other papers in this category. Is it basically standard to use GANs right now? Because whenever you want to generate, large scale images, typically people reach for GANs. So is that sort of the preferred approach?
Well, you don't have to be familiar with the literature. You just have to look at the method names. They're ATTN GAN, DM GAN, and DF GAN. So
right.
Yeah,
I wasn't sure. I wasn't sure if it's comprehensive. But yeah, that's why this paper is kind of interesting to me, because it is the first, I would say, autoregressive approach to generating, large images.
It's not the first. So Scott Reed also had some work on using autoregressive style models to generate images, but those were a few years ago. I think his last paper on that topic was maybe 2017 or 2018, I want to say. And most of the work since then has focused on using GANs. Mm-hmm. Yeah, so that's pretty much it for the topics in the paper. Yeah. Oh, I guess the last part in the evaluation is that they did a human study. And this is really important for any time you're generating images. Because as we said, the FID and the inception score, these automated metrics for measuring image quality, are not that great. And I usually trust human perception more. But in addition to taking Aditya's word for it, which is great, they also did a user study on Amazon Mechanical Turk, which is, in my opinion, kind of the gold standard way to evaluate these kinds of models. So it's good to see them dotting their I's and crossing their T's.
I don't know. I kind of just find it really hard, to be honest. I mean, it seems to me like it tries to look scientific, but at the end of the day, you're like asking random Turkers like which image looks better. And it's like such an undefined question in my mind, like better in what? Like more realistic texture, or is it, like which image is more realistic? Like in what sense? Like the content of the image or the textures of the image? Or I just feel like it's a very, I don't know, I don't find it very convincing, and I'm not sure that the Turkers really understand what's being asked here potentially, or that they are giving us the results that we think they are giving us.
Yeah, like it's not perfect, but I think it's the best among the alternatives that we have. Because the inception scores, the automated metrics are pretty well known to not correlate very well. And we can't just take the author's word for it that our samples are the best. So it's not perfect, but it's the best we have.
I think I'm like pretty happy with, say, like figure 3, like showing just side by side some uncherry-picked captions going to images. If I'm just given a large batch of uncherry-picked examples, that to me is probably the best evaluation at this point. And I trust that a bit more than some AMT sort of exercise.
Yeah, I think the other thing that's useful to keep in mind about these AMT user studies is that it's very easy to get a very large margin here, because if your model is just consistently a little bit better than the other one, then like 99% of users will prefer yours. And that's so it's a different sort of metric than we're used to seeing in other cases, where actually you only need to be a little bit better than the other one in order to get like 100% of people to prefer your method.
Okay. So we're about 1 hour and a half in. Is there anything else that we want to say about the paper, or should we just start maybe taking some audience participation at this point?
Yeah, I think that's pretty much all I had to say about the paper. Obviously, it's super cool with amazing results. And thanks, Aditya, for joining us today and helping us walk through this great work.
Oh, thanks for inviting me. It was great speaking to you both.
Great. Yeah, I do feel like maybe some conclusion is kind of necessary here, like on a high level. And in terms of like, the conclusion of the paper, and also like what are some of the next steps? For example, Aditya, like what are you excited about? Like where do you want to take some of this work?
I guess there's a lot of potential directions. Maybe V2 of the model, or starting to work on video modeling maybe. But I still haven't decided on anything concrete yet.
Mm-hmm. Yeah, I think the conclusion for me on a high level, to me, the most interesting thing here is that we are putting text and images into sequences of integers and using transformers to model them. And here, as also the case in GPT, we are scaling these transformers and getting better and better at modeling these sequences of integers. And I like this idea that we're taking a lot of different problems through this integer sequence bottleneck. And I think that's going to help with a lot of modeling problems in AI. And I like autoregressive models for images a bit more than GANs. I'm a little bit afraid of GANs, so I'm okay using them for patches, but I'm always like slightly squeamish because I know they drop modes. And so you're not getting what you want or think you are. And they're sort of deceiving in that way. So I sort of prefer this approach by default, and I'm glad to see that it's working really well when you scale it up.
Yeah, I think there's that technical bit about, VAEs and autoregressive modeling of integers being a really great technical tool. I think I also just love the problem setting being explored in both DALL-E and Clip that we've been talking about the last couple episodes. That in general, this idea of making progress in vision by having connections between vision and other modalities, and most especially language, just feels like the right thing to do. It feels a lot of times like vision and language is sort of treated as a sideshow in computer vision, and it's a set of problems that we can work on, but it's not really the main story. And what is most appealing about me for this line of work is that it really puts large-scale multimodal vision plus language at kind of the heart of lots of amazing advances in both computer vision, and then in this setting, also like computer graphics of generating new images from scratch. And this idea of putting multimodal vision plus language at the heart of everything, I think is very appealing and probably will continue going forward.
Although what I find fascinating here is that the multimodality only enters at the dataset. Like actually this work subtracts away the multimodality. It's just a sequence of integers to a large extent. Like I know we're modifying some of the attention masks and so on, but that's really like not the important thing here. Like what makes this work is actually the subtraction of the modality sort of characteristics individually, which to me is fascinating.
You can't just say that, it only enters through the data. The data is the most important part. And the fact that you have this
Sure.
multimodality is what allows you to collect a data set of this scale and variety, and what allows you to tackle this problem at all in the first place.
Okay, sure. But it does enter sort of quote unquote only at the data set. But I think the models are so general that they don't actually care what modes are being represented and what modes are being plugged in, or what modalities, I suppose, are plugged in, which to me, that's the fascinating part. Mostly.
Okay, that's fair.
Because again, like we can imagine, we want to throw in videos, we want to throw in audio, speech, text, and so on. And so, you want to, and this is sort of like giving you a recipe or a template to follow to approach a lot of multimodality projects, I would say. And a lot of them would it's very obvious how you would treat any of them if you can collect a large enough data set of those correspondences.
Yeah, definitely. I think another big takeaway for me on this paper at a high level is that machine learning plus systems is probably here to stay. That sometimes it feels like people just want to live at the algorithm side and live in the land of real numbers and perfectly pure algorithms and kind of forget how they're being implemented on machines. And you really can't do that. When you want to move to really big scales, really big data sets, achieve really impressive results, it's really critical that you're not just a computer vision practitioner. You're not just good at thinking about loss functions, but you also need to be really good at the systems engineering aspect of these things. And I think that's something that will continue to be the case going forward. Mm-hmm. And then even more particularly, I think this paper a little bit serves as kind of an advertisement for some of the next generation pieces of hardware with more memory in the GPUs and maybe different floating point formats that might help to alleviate some of the concerns that were raised in this paper. But that's not to say someone else will duplicate this model on the 80 gig A100 GPUs next year that NVIDIA has. But all these tricks around parameter sharding will still be useful. It'll just let you train bigger models to kind of reach a new limit of those larger next generation hardware platforms.
Mm-hmm. Yeah, I think it's definitely interesting that machine learning for a long time was sort of in the realm of, or like, if you wanted to be at the bleeding edge, you were talking more about the bleeding edge in terms of the algorithms. But now if you actually want to get really strong results, you have to be at the bleeding edge of the high performance computing aspect of actually training these models. And that is probably here to stay, especially because we are seeing that we have enough data and that these models are not plateauing out, and they continue to give us better performance as we scale them up. And so this high performance computing sort of aspect of AI is sort of here to stay, and wasn't always here, because the models that we were using previously were sort of upper bounded by human design, and that's not the case anymore. Like, we have designs that are now upper bounded by the compute available. So what a fascinating place to be.
Yeah, absolutely. So with that, with that more proper conclusion, should we invite up some audience members? So our disclaimer is that we actually would like to release a version of this conversation after the fact, sometime next week, as either a podcast or YouTube video or something like that. So our disclaimer is that for anyone who wants to come up as a speaker, we'll ask you to affirm that, either say yes, you're okay with being in the recording, or no, you'd prefer to be edited out of the version that we release. So that's something that we'll ask of all the speakers as they come up.
Yes, and in the previous episode, we did end up obtaining a written consent from everyone, and so we would like to continue that. So if you speak, you can help us out by reaching out to us, but we will also try to find you. So let's invite up Ian.
Hey, how's it going?
Hi, Ian.
I was curious to go back to, thanks for focusing on these, by the way, and thanks for the great work, Aditya. I would love to go back to the VQVAE part, and kind of go into the details of some of the decisions there. I believe it was mentioned that the Gumbel softmax here was without the straight-through estimator. Was curious basically why, and also, how deep you went, Aditya, on the different tricks that you would use if it was a more conventional VQVAE with like codebook restarts, and there's sort of a whole dark alley of rabbit holes there, of those tricks. And if you found that the Gumbel softmax side was preferable, because it seems to me that we have a lot of hyperparameters and a lot of tricks, both for sort of the VQVAE approach or the Gumbel softmax approach. So anyway, really curious what everyone thinks about that.
Yeah, I would say you could use either. It's just I personally didn't like the email loss and the dead code revival and that sort of stuff. So while others were looking into it, I wondered if I could just hack a discrete VAE well enough to work stably. But I think maybe the one advantage is that it does scale to larger vocabulary sizes more easily. So I think from the experiments that Wu and others tried, you get a lot of dead codes when you scale up to something like 8K vocab size, and the behavior is a little better with the discrete VAE.
Interesting, and the restarts and that sort of thing, didn't help there. I guess one specific question I found on the restarts is interesting is, do you do the restarts randomly, or do you do the restarts near other embeddings? I think, Andre, in your VQVAE version, I believe your initialization was kind of it was similar to a restart, but you just did it once at the start.
Yeah, so when I was re-implementing it, I found it really important to do data-driven initialization, similar to what you would do. Really what's happening here is that the bottleneck layer, we have a k-means, right? And the same objective. And all the k-means tips and tricks apply, like reviving, clusters and stuff like that. So I found that it was pretty important to initialize with k-means, and then to also potentially include the dead code revival, though I did not implement that. I think in my personal experience, the Gumbel softmax, I find it more appealing algorithmically, but I find empirically the VQVAE version from DeepMind, for me, currently works better, just when I look at reconstruction loss. And so it is slightly more gross, but it just works for me so far. But I think it's a hyperparameter tuning exercise to a large extent, and you do have a clear objective that you're trying to optimize. So it's just really an empirical question.
Yeah, that's a trade-off. You're trading off the complexity of the dead code revival and the other stuff for hyperparameter tuning, basically.
Right. That's a good way to put it.
Another aspect of that I was kind of curious about is there's been a number of hierarchical VQVAs from Jukebox back to VQVA2. I was curious. The implementing it here would be a little bit hairy because of the conditioning, but curious if anyone had thoughts on that.
Why would it be harder to implement here than say for Jukebox?
I guess if you did it Jukebox style, it would be easier. But the VQVA2 implementation would be interesting because you're not training the different levels separately. I thought that was like a very nice simplification in Jukebox.
Yeah.
But yeah.
The problem with these hierarchical approaches back when we were experimenting with them is that if you have a top level code and a bottom level code, like let's say in a two-stage VQVAE, I think it often happens that all of the information goes to the bottom level code and the top level code ends up learning nothing. So in order to prevent that, you would need to apply various tricks and stuff like, I don't know, using dropout sometimes to not use the bottom level code in order to force the top level code to capture some of the information. So Hibu's idea to just use separate VAEs is quite nice. If I were training like an upsampler for DALL-E, that's probably the approach I would use.
Yeah, I think the VQVAE2 style sort of approach makes sense. It does complexify the code base, of course, because now we have multiple levels of discretization, and just balancing it and implementing it seems kind of hairy. But I do think it sort of makes sense.
Yeah, I think the hierarchy to me seems like a necessary evil, that if you're unable to get the image quality or the speed of sampling that you'd like, then some kind of hierarchy could make sense. But the fact that it works so well without the hierarchy is part of the appeal of the approach here, in my opinion.
I guess I would expect that the hierarchy should be able to get away with slightly smaller models, because like as you're generating the image and you're generating the 700th token in the 700th patch, you're attending to all the other patches that already exist, and you have to sort of redo the job of image recognition in the weights in order to sample the next patch. And so it seems to me like if you arrange it hierarchically, you're giving yourself some of that information potentially in a more immediate fashion without having to do sort of this recognition sort of de novo at every single next token, if that makes sense.
But you have fun stuff with multiple code books and all of these other things. Actually, that reminds me that one thing I've seen in a number of these works and kind of experiment with is it even in the single layer and the no hierarchy version, like this one is, do you keep two different code books for the two different stages? As far as I can tell, I'm curious, Aditya, on this one, whether it was the same code book. I just mean like you could have shared indices but different embeddings. Use one set of embeddings for the first stage and then another, sometimes like larger for the second one.
Yeah, I think in the past when I trained up samplers, that's the approach I took.
All right, great. Thank you, Ian, for the question. Let's see.
Hi there.
Hi, Paul.
Yeah. So I'm coming at things from the perspective of human vision, theoretical neuroscience perspective, and what's known about the mechanics of human vision. And one of the areas that's really not understood at all is how scene understanding happens, how scenes are represented in the brain. And even in computer vision, it seems that scene understanding is at a pretty crude state, maybe geometric object kind of models. But this seems to have a lot of semantic understanding. And, GPT-3 seems to sort of capture a lot of human knowledge in its language model. And what's been able to be generated with these images seems to obviously capture some semantic sense of things. Would you say that this has progressed in some way a framework for how scene understanding and representation could be working?
I don't know. I feel like I just trained a big model and it worked, so I'm not good at commenting on these sorts of things.
Okay.
I mean, yeah.
What I was going to say on the topic, I think partly, is that, the whole grail of basically AI to some extent is to find these general purpose learning algorithms that we think our brain implements in a very multimodal way in the brain. And I think these transformer models to me are sort of barking up the right tree, where we are seeing a lot of very powerful representation learning on arbitrary modalities. So I would say, I don't know if we are, how close we are, or if we can even measure the distance function in some meaningful way. But I find it very appealing from that perspective that we are seeing some very powerful general learning algorithm, regardless of the input modality. And I find that kind of encouraging on that high level. Yeah,
there's that. I also think that one plausible avenue you could imagine working with is that, if something like Clip or DALL-E might be really good at scene understanding, and then it's like a thing that's really good at scene understanding that we can poke and prod at much more than we can a real human brain. So one kind of direction of research that, some people are doing already is you take these models already and then try to correlate their representations in some way with what's going on in the human brain. and kind of use these big models as a proxy for what might be going on in our minds. I'm a little bit like, that's an appealing direction. It's nice to see people working on that. I could definitely imagine that happening again for these types of models. But I'm always a little bit skeptical that we end up thinking our mind is too similar to whatever is the fancy technology of the day, right? Like if you look historically, there were analogies around our minds working like a set of gears back before there were computers. And then as soon as we had computers on the scene, we had analogies like from Alan Turing and others that our mind must work like a digital computer. And now that we have things like DALL-E and GPT-3, there's a sense that Andre is putting forth that maybe our minds are working like transformers. And previously, every analogy we've had for what our mind is working with has become deprecated by the next fancy technology. And I think that will probably happen here as well.
Sounds good.
Yeah, for now it looks like we're kind of riding this wave of technologies made possible by the transformer, but it's hard to say where things will be at 5 years from now. But I agree, it's really nice to have like a single unified interface for everything.
It would certainly be intriguing to get some insight into what the higher level representations are that are allowing one model to convert into the other model and to get something meaningful out.
Makes sense. Yeah, I don't think we sufficiently debug these models on a high level, and or try to like sort of understand them and so on. There is quite a bit of literature on understanding convolutional networks and so on, and also, by the way, in the case of transformers, I have seen some papers, but I think ongoing work, I would say.
Great, thanks a lot. You can go to the next one.
Okay, thank you. Let's say hi to James. Hey, James.
Yeah, so I mean, I'm more of an infra person these days. And so I guess what I'm curious about is things like the experience of like going back and forth between having to work on optimizing the infrastructure and like solving these like non-mathematical problems in like compression and precision, and doing the actual science, and sort of how that worked out, and like, was it the same people or different people, and like, I don't know, just I'm curious how that worked out.
Yeah, the implementation was me, Mikhail, and Scott. So we kind of did all of that. I did all of the model implementation. And once it got to the point where we started doing the distributed training, Mikhail first started looking into Power SGD, and Scott wrote a super fast orthogonalization kernel. And then I kind of took it the rest of the way there with the 12 billion model. But yeah, it was just a team of three of us.
Did you ever consider using TPUs, given that I know you used the like Google GPU clusters?
It was used for IGPT, but I think after that we weren't using them anymore. So it probably would have been very expensive to, switch to it for a one-off project.
I guess one reason I brought that up is just like, in my experience, the world of ML on TPUs, especially ML on TPUs at Google, and the world of ML on GPUs, especially outside Google, there are a lot of differences, but one of them is this sort of a philosophical difference about the breakdown between sort of model work and science and engineering work and infrastructure. And so a lot of the things that are that like the paper talks about in terms of distributed training and like parameter sharding and mixed precision, like in TPU land, it's not that we don't have similar problems, but I think we often treat them as they're compiler problems. They're problems for the compiler team to solve. And because they're kind of orthogonal to the problems of like the model and the science and the math. And I just don't know whether that's a better way of doing it, a worse way of doing it. It sounds like there are trade-offs, like the distributed communication methods that you used could be tailored exactly to the model, but also there would be benefits to like model teams not having to dive super deep into the implementation all the time.
Yeah, it definitely adds a lot of cost to pursuing a project like this. Like doing all the work to get it 100% there, it involves just a huge amount of work. And in the meantime, what if you get scooped or something before the release happens? So, yeah, I think it's definitely a trade-off. It would be nice if in the future things just were automatically handled by the compiler and we didn't have to worry about all of this.
Yeah, I think it's a very interesting question. If it's a compiler problem, I think it's a very ambitious compiler problem, right? Like there's a lot going on here, not just in the mixed precision, but also the distributed components and also their interaction. Doing that in a general case.
One thing I'll mention and then I'll disappear is this parameter sharding optimization. So I think the first time it was written about publicly was in Microsoft's Zero paper. And then it was also adopted, like NVIDIA has a library for it, and there's like some progress in upstreaming into PyTorch. But the first time that it was used, as far as I know, it was actually added to the TPU compiler. So this was written about in a paper like in 2019, but I don't think that anyone in the science side of the ML world paid attention to that or noticed it. And because it was something that the TPU team treated as like an implementation detail, it never got into the like discourse on like different training methodologies that researchers have. So there's even like drawbacks to this in the like research credit assignment sense. Anyway, thanks. Maybe I should do like a TPU clubhouse someday.
Yeah, for sure. Okay, thank you, James. Okay, maybe like one more or like two more. There are two people who had like their hand up for a very long time. Let's say briefly hi to Akram.
Hello.
Hi.
Hello.
Thank you very much for taking my question. My question is a bit like high level on transformers. So given that the text here is not that long, I want to see is transformers right now is kind of the starting point for any task that we're dealing with text. For example, why we're not using LSTMs here.
Yeah, I think LSTMs have been pretty well deprecated at this point. And one of the big problems here is scale, is because something like an LSTM has a sequential dependence on the text at training time, that because the hidden state at times t depends on the hidden state from time t-1, that you can't parallelize the processing over the tokens in the sentence. And that makes it very challenging to scale something like an LSTM to a model of the same size that we see in this paper. So I think the transformer approach to processing text makes it much more parallelizable and therefore lets you train much larger models.
Okay. Thank you very much.
Mm-hmm. Yeah, thank you for the question. I think in this case, it's actually kind of interesting because we are just conditioning on text and we're not generating it, of course. So you could imagine encoding the text with an LSTM and feeding it into the transformer, but I would expect that to just basically work worse. Like fundamentally, you're going through this hidden state and you have so many sequential steps, and it just seems like these encoders are just not very powerful. And so it will just not work well.
Also like LSTM is just such a funny architecture. Like it's so Baroque, but a transformer is somehow much cleaner in that you're just sort of comparing everything with every other thing with a pretty straightforward type of bilinear operator, and then have MLPs on top of that. And it's kind of a cleaner architecture than an LSTM, I think. Yeah,
it's more of an all-to-all to all the tokens, whereas LSTM is forced to sort of function serially and really just like compress a lot of information into a fixed hidden state vector. It's just not appealing, basically, and it doesn't seem to work well empirically. Let's finally say hi to Mohsen because he has had his hand raised for a while.
Hi, thank you for the great program. It has made our Sunday evenings very enjoyable. The question I have is related to the training data set that has been discussed a number of times here. Given the background I have, is what is the value of generated data samples for training such large models? In the sense of if you have ways of controlling the scene, and having control over complex object occlusion or the left or right, using traditional computer graphics. Is that dataset going to be helpful for training such models? And if yes, what is the value of one or is a series of these generated samples compared to a real data point that we get from crawling the web, a la the data sets that was published on conceptual caption?
I guess the data that's most useful is whatever the model doesn't know how to do already. I guess broadly was your question more about like when training the model, what's the value of additional data?
Additional generated data. Let's say you could create a number of scenes in a game, in a hyper-realistic rendering environment, and you could change the relationship of those or the occlusion of those, or even the camera angle, lighting, all those sorts of controls that you have over synthetic data.
Yeah, so I actually built a data set kind of that flavor a few years ago called Clever. It was not for this task. It was not meant for this task of text to image generation. It was instead meant for this task of question answering, especially with very complicated multi-stage questions. And there we kind of had the same intuition as you that if you're fully in control of the data generation process, then maybe you could just generate a lot of data that kind of either covers all the blind spots in the model or at least lets you diagnose the blind spots in the model. But I think from my experience in that project, it's really tough to generate synthetic data that actually covers the full scope of things that you'd like to do. So it's pretty good. We can get photorealistic renderings, and that works pretty well. But the hard part to generate automatically in these data sets is both realistic language and also realistic scenes with interesting compositions of objects. Because in general, these models can't work for all possible data. Instead, they're learning some kind of bias about the appearances of objects and correlations of objects that tend to occur in the real world. So if you have a fully synthetic data set, it's like the statistics of the scenes that you're going to generate are not going to match the statistics of the scenes in the real world. And it's very difficult to close that gap.
Yeah, thank you for the question. I think it's extremely interesting because, like Justin pointed out, Clever was basically it was a rendering of different scenes and environments with all kinds of complicated properties. And like Aditya mentioned, this model particularly is struggling with positional relationships and, say, counting. So is it possible to maybe render a ground truth when it is expensive to obtain at scale on the internet? And is there any positive transfer to be gained from training on the simulated data for the model to really understand these concepts from the free data source, basically?
Yeah, that's a super interesting question. If that's possible to do, it would be very helpful.
Yeah, thank you for your insight. It is good to know what the parameters around that generative or the synthetic data generation is going to be to stay close to the statistical properties of the real scenes that we are seeing. And that's a topic that I would love to hear more about.
Yeah, I think another thing here is that it kind of combines with maybe compositional generalization abilities of the model, right? Because like maybe you could Clever was this blocks world situation with like blocks that occur, and they're not like animals or people or any realistic scenes. They're just kind of three-dimensional blocks. But if looking at blocks is enough to understand relationships like the red block to the left of the green block behind the blue block, and then transfer that to compositions of not blocks but real objects that you'd see in the world, that would be really interesting. And it seems that something like DALL-E has a little bit of this compositional generalization ability that we'd like. But the more compositional generalization the model can do from its training set, maybe the better hope we have for these kind of synthetic pieces of data to cover the blind spots in the model.
Thank you, Mohsen.
Thank you.
I actually think OpenAI is no stranger to sim-to-real transfer, of course, in their robotics project. So I think this is actually a pretty fascinating kind of avenue of future work, potentially, where you have some subset of real data, and then you pad it out with infinity of simulated data and try to get the transformer to really learn about all these concepts from there. So that would be pretty cool. Okay. So I think, Justin, we are 2 hours and 15 minutes in, so I think this is a good time to maybe wrap things up.
Yeah, sounds good.
Great. So thank you, everyone, for joining us. Thank you very much, Aditya, for also joining us as a co-host today. It was really incredibly interesting to hear a little bit of the backstory of this fascinating project.
Definitely. Thanks a lot for having me.
All right. Thanks, everyone.
Yeah, awesome. Thank you.
See ya.
Bye.